Welcome to this lecture. We are going to discuss we are going to discuss dynamics of first order systems. Specifically, we are going to see the sinusoidal response of a first order system. For first, we'll give an sinusoidal input to a first order system and see what is the response. So this is the first order system and this is sinusoidal input. Sinusoidal input is, how do you write sinusoidal input? A sin omega t, where A is amplitude and omega is frequency. More details about the sinusoidal input has been discussed in my previous lecture titled as PC45. Titled as PC25. So this lecture gives complete more information about sinusoidal input, how do you write sinusoidal input, and what are its features. Now let us find the response of this first order system for this sinusoidal input, A sin omega t. The usual procedure, take Laplace transform of this, x of s equal to Laplace transform of sin omega t is omega by s square plus omega square. Now substitute in the transfer function y of s equal to g into x, so that is k by tau s plus 1 into a omega by s square plus omega square. Now next step is you have to find the inverse of this. So how do you find inverse? Inverse Laplace, we'll take the root of partial fractions. So we'll split this into partial fraction. We'll split this term into partial fraction. We'll split this into partial fraction, estimate the constants, and then find inverse Laplace. If you write this into partial fractions, this term, there are two terms in the denominator. So c by tau s plus 1, and here this is a second order term. So ds plus e by s square plus omega square, where c, d and e are constants. So you have to evaluate these constants c, d and e and then take inverse Laplace. So let us multiply the whole term, left hand side and RHS, by the LCM. So if you multiply, what do you get? If you multiply by the LCM, you will get this c into s square plus omega square plus ds plus e into tau s plus 1 equal to, here the numerator is ak omega. C, D, and E are constants. Now, how do you evaluate these constants C, D, and E? You can either substitute some values for S, or you can compare the like terms on both sides. So first let me substitute S equal to minus 1 by tau. So that will make this term 0. Tau s plus 1 will become 0. So the remaining term c into s square, 1 by tau square, when you substitute s equal to minus 1 by tau, plus omega square equal to ak omega. So if you solve for c, you'll get ak omega tau square by 1 plus omega square tau square. Now to find the other two constants, let me compare the like terms. First let me take s square terms on both sides. So let me compare s square terms. So here you have s square, c s square c, and here you have ds into tau s. So d tau. So s square terms here are c s square c and d tau. On right hand side there is no s term. So c plus d tau equal to 0. C plus d tau equal to 0. Because on right hand side there is no s square term. So that means that gives you d equal to minus c by tau, and c already you have evaluated. So if you substitute here, d equal to minus ak omega tau by 1 plus omega square tau square. So next let me compare s term. So let me compare s terms. What are the s terms here? There is no s here. There is ds. There is ds into 1d and then e tau. So d plus e tau, the left hand side. Right hand side there is no s term. So d plus e tau equal to 0. That is got by comparing s terms. So e equal to minus d by tau. D is already evaluated here. D has got a minus sign, so e minus of minus will be plus ak omega by 1 plus omega square tau square. Now let me substitute this value c d e in this expression. Let me substitute c d and e in this expression. This. I'm going to substitute c d and e in this. C by tau s plus 1 and I'll write this as two terms, ds by this plus e by this. So if you do so, you get y of s equal to ak omega tau square. This is the first term, c by tau s plus 1. And this is the second term d and e. This is ak by 1 plus omega square tau square. I written common, which is common for d and e. ak omega by 1 plus omega square tau square. So the remaining ds is here I have taken only ak. So what is left is omega tau. So minus omega tau s by s square plus omega square. D has got a negative sign, minus sign. So this is ds by s square plus omega square. And this is e by s square plus omega square. So e is this ak omega by 1 plus omega square tau square. So this is e, which I substituted here. The common factor ak I taken out here. Right. So I just substituted c, d and e in the equation for ys. So now let me take inverse Laplace. If we take inverse Laplace, this term, first term inverse Laplace is this. These are all constants, so retained as such. 1 by tau s plus 1 inverse is 1 by tau into e power minus t by tau. So this is the inverse of this. Now the second term, again this is common, retained constants retained as such, ak by 1 plus omega square tau square. Now here if you see minus omega tau is a constant. Next what is there left? S. So s by s square plus omega square. S by s square plus omega square is what? Inverse of that is cos. Inverse of s by s square plus omega square is cos. And inverse of this omega by s square plus omega square is sine. Sine omega t. So this is after taking inverse. Y of t equal to is the first term, second term, third term. Now you have two terms on the RHS, three terms on the RHS, 1, 2, 3. So if you see, okay, now the second and third term can be simplified into a single term by using the trigonometric identity p cos theta plus q sin theta equal to r sin theta plus phi. These two terms, cos plus sin, can be simplified by this single term, by this trigonometric identity. P here is minus omega tau and q is 1. Q is 1, p is minus omega tau. So if you simplify using this identity, it will give you single term r sin theta plus phi, where r is root of p square plus q square. Root of p square plus q square. P is this, q is this. And phi equal to tan inverse of p by q. Now let us substitute. P is minus omega tau, q is 1. Let us substitute r equal to root of p square plus q square. P is minus omega tau. So p square is omega square tau square. Q is 1. Q is 1. So plus 1. So r equal to root of omega square tau square plus 1. And phi equal to tan inverse of p by q. P is minus omega tau. Q is 1. So tan inverse of minus omega tau. Tan inverse of minus can be written as minus tan inverse of omega tau. Minus can be taken out. So tan inverse of minus omega tau is the same as minus tan inverse of omega tau. Now, so the second and third term I will simplify into a single term by this. This is the first term. I just substituted into the previous equation. First term written as such. Only thing is this tau square and tau I simplified. Taken written as tau here. This is the first term. Second and third term, I retain the constants ak by 1 plus omega square tau square. Then this is r. This is r. This is r. R into sine omega t. Theta is omega t. Theta is omega t. This is theta plus phi. So the previous equation simplifies to this, y at t equal to this. Now if you find there are two terms, first term, second term. So now what happens for large values of t, as t tends to infinity, t tends to infinity means for large values of t, maybe t equal to 4 tau or 5 tau or 6 tau, even 5 tau also. Even if you consider t equal to 5 tau, you will find this term becomes almost 0, the exponentially decaying term. So for large values of t, or as t tends to infinity, the first term in the RHS vanishes. So at such condition, only the second term exists. So for large values of t, we call it as, we can ignore this first term and take only the second term, and we call this as steady state solution of the response, because after some time this has no meaning. This is almost 0, first term. So after some time only the second term will exist, and the steady state solution at steady state is this. Write only the second term, and second term is, so at steady state only the second term exists. The second term is y of t at steady state. Yes, means at steady state equal to this constant, and this one root of 1 plus omega square tau square. If you simplify this becomes root here, ak by root of 1 plus omega square tau square into sine of omega t plus phi. So this is a final or steady state solution of the sinusoidal response. I have just rewritten that, and I just printed this again, the same equation printed here, typed here. At steady state, y of t equal to ak by this root of 1 plus omega square tau square into sine omega t plus phi, where phi equal to minus tan inverse of omega tau, as we found here, minus tan inverse of omega tau. So this is the response equation of a sinusoidal input to a first order system. For a first order system, when you give a sinusoidal input, the dynamics, the response is this, and the dynamics will be represented by this equation. So this is known as the sinusoidal response equation of a first order system, right? So this has got importance, sinusoidal response. So what are the features of this sinusoidal response? What are the important aspects, features of the sinusoidal response? We will continue this and discuss this in the next lecture. So till then, see you. Bye.